In this section we're looking at the intersection of two planes in three-dimensional space. We actually have three different situations that can occur. We can have two planes that are parallel to each other but are distinct, and in this case we have no intersection points between the two planes. Next case is where the planes are parallel and coincident. So in this case they're actually the same plane, although their equations might look different. We had a similar situation when we looked at the equations of lines, where we had two parallel lines that were actually coincident. So in this case we should have an infinite number of intersection points because the two planes are really the same plane, they're on top of each other. And the third case is where the planes are not parallel, and here what happens is the planes slice through each other and actually intersect in a line. So in this case we also have an infinite number of intersection points, but it's different than the previous case where the infinite number of intersection points come from the two planes being on top of each other. Here they just share an infinite number of points lying on a straight line. And so when we find the solution to this system of planes, we should end up with the equation of a line. Before we look at the algebra of actually finding intersection points, there are two things I want to point out. One is that we're going to consider the planes in their scalar form. So we're always going to be looking at the scalar equation of the planes when we do the algebra to find intersection points. So in this case, where I have two parallel planes, you see that the planes have been given in the scalar form. So I have scalar equation of each plane. The next thing to point out is that the normal vectors are an important part of telling us which situation we have. So if I identify the normal vectors for each of these planes are actually labeled plane 3 and plane 4. So I'm going to call it normal vector 3. And remember, the normal vector comes from the coefficients of x, y, and z. So the normal vector for plane 3 is 2, minus 6, and 4. Similarly, the normal vector for plane 4 and 4 is 3, negative 1, and 6. So just by inspection, looking at the coefficients, the components of these two normal vectors, I can see that normal vector 4, is actually just 1.5 times normal vector 3. That means that it's a scalar multiple of normal vector 3, and if it's a scalar multiple, therefore the normals are parallel. So normal 4 is parallel to normal 3. If the normal vectors are parallel, that means we either have a situation where the planes are parallel and distinct, meaning no solution, or they're parallel and coincident, meaning we have an infinite number of solutions. Let's take a look at situation B and confirm that also. So here the planes are labeled plane 5 and plane 6. So normal vector 5 is equal to 1, 1 minus 2. And normal vector 6 is 2, 2 minus 4. So it's quite easy to see that normal vector 6 is equal to 2 times normal vector 5. So normal vector 6 is a scalar multiple of normal vector 5, and therefore the normal vectors are parallel. And we can also write that the planes are parallel. So plane 5 is parallel to plane 6. That's something that I could add up above here. Plane 4 is parallel to plane 3. So in case A and case B, the planes are both parallel. One way of proceeding in situation A, to show that the planes are distinct, is that we could find a point on plane 3 using a table of values and then substitute it into plane 4 and show that it does not satisfy plane 4. So that's one approach. Another approach is to take a look at the d values. If I have an equation of a plane that I scale up to create a parallel plane, so in this case I scaled up the coefficients of x, y, and z by 1.5. If I want to create the same plane, meaning the planes would be parallel and coincident, I would have to scale up the d value by the exact same amount. So if the original d value was -7 and I scaled up by 1.5, then this d value should have been -7 times 1.5. So this d value is equal to -2, and it's clearly not equal to 1.5 times -7. So just by looking at that d value, I can tell that the planes are distinct, because the d value would have had to been scaled up by the same amount. Let's take a look at situation B. So the claim here is that these planes are parallel and coincident. We know they're parallel because we already looked at the normal vectors. Take a look at the d value. So d value for 5 is equal to 2. D value for 6 is equal to 4, and that's equal to 2 times 2, or 2 times d value 5. And that's the same scalar that I had for the normal vectors. So if I scale the normal vectors up by a scale factor of 2, I've scaled the d value up by a scale factor of 2, that means plane 6 is really the same as plane 5. In fact, if you look at plane 6, I could divide each term in this equation by 2, and I would get back to plane 5. So it's quite easy to see, once we've looked at the normal vectors, if we have either a coincident situation, like situation B, or a parallel situation, like situation A. The last case that we want to look at is situation C. And as I noted before, these planes are not parallel, and so they will intersect in a line. Still an infinite number of intersection points, but intersect in a line. Let's take a look at the normal vectors. So normal vector 1 is equal to 2, -1, 1. Normal vector 2 is equal to 1, 1, 1. And clearly there's no scalar that would work for all three of the components x, y, and z. So moving from 1 to 2, I've multiplied by 2. So moving from 1, I would have to make this a 2 and also make this a 2. So clearly these are not parallel vectors. Put a slash through that, so n1 is not parallel to n2, and therefore plane 1 is not parallel to plane 2. And therefore I can conclude that plane 1 and plane 2 will intersect in a line.